Hello, everybody. As was said, my name is Evgeny Mandrikov, and today we're going to talk about Java code coverage and their best friend Bytecode. There will be a little bit of scandals, a little bit of intrigues, and investigations. Before we start, I should tell you some disclaimer. I work in a great company, Sonar, creators of SonarQube, SonarLint, SonarCloud. You might know them. By the way, let me do a quick check. Do you use our products? Wonderful. Don't be shy. I don't care if you hate them. Because whatever I'm going to tell you today is not at all about my work, or not my primary work. It's all about what I do for open source, my free time at night. So this has nothing to do with my employer. At my free time, I work on a wonderful library or a tool called JaCoCo. You also might know it or not. That's fine. This tool allows you to measure Java code coverage. And we're going to talk about interesting things in Java that came out of this work. While developing JaCoCo, we tested on quite wide range of JDK versions for different Java compiler versions. If I'm not mistaken, as of today, it accounts for 17.5 JDK versions. Why half? Because we also test early access builds. Why we do so? Well, because we do find some bugs. And funny fact, I could even say that most of the time we find bugs not in our tools, but in JDK itself. If, again, my memory is correct, around the time of Java 9, we've been one of the top open source contributors of bugs in JDK. They get fixed, and of course, sometimes we do implement new features in our tool. So, for example, for some code base, code coverage report with JaCoCo version 0.8.9 some time ago looked like this. While looking on this report, you might say, well, there is not enough tests. So there is some uncovered code, so probably it's not well-tested application. Well, we implemented some new features in JaCoCo, and starting with JaCoCo 0.8.2, exactly the same code base, exactly the same tests, started to generate following report. Everything is tested, 100% coverage. Why this happened and what those new features are about, that's exactly what we're going to talk today. And before we start, it's really important to understand that JaCoCo receives all of the information from the class files, from the bytecode, not from the source code. This is an interesting property because it heavily simplifies integration. We don't need to recompile your files. We can easily integrate into already compiled code on some application server, etc. Absence of source files is not a problem. You can measure code coverage for some library for which you don't have a source code. This is nice. Also, this helps us, developers of this tool, cover a new syntactic sugar in the language, which does not change the bytecode. Some examples of this is text blocks, which appeared in Java 15, or there is some other drafts like concise method bodies that wouldn't change anything in the bytecode, which would change only the source code. It's not a big deal for us to support these new features. And at the beginning, we thought that this is a nice way that opens us a door to other JVM languages such as Kotlin, Scala, Groovy. Why this doesn't hold true anymore, maybe you would see today. We will see some examples why this doesn't hold true even for Java. And here is a real disclaimer. Sorry for this, there will be a little bit blood out of JVM. Sorry for this, we're gonna use today naked Java compiler, no IDE, no Maven, no Gradle, no Spring Boot, nothing. Command line only. Sorry for this, we're going to talk strong language. We're not going to talk English today, we're going to talk bytecode. If you are not ready for this, maybe you have still time to go and visit another session. And sorry for this, within remaining 30 minutes, I will try to do an intense violence of your brain. Again, if you're not ready, let's go and all together listen some other wonderful session. So, are you ready? Okay, let's start. Let's talk about Java. Let's start with something pretty simple, pretty basic. Let me have an empty class, and let's me call it bless me. Why not? Who agrees that this class is empty? There is no fields in it. There is no methods in it. It's empty, right? Who thinks that it is empty? I do think it is empty. Okay? Who thinks it is not empty? Okay. Who are all other people? It depends. Okay, wonderful. Who thinks it depends? Okay, some other people. So what we are going to be doing today, we will be compiling this code, so Java C, bless me, and we are going to be looking at its bytecode. Java P, standard tool part of JDK, with two arguments, with two options, -v verbose and -p, show me privates, protected, etc. Together, those two options, this is two my favorite options, I call them show me everything. Java P, -v, -p, and a class name, bless me. And here we see some meta information about class file. When it was created, it's MD5 checksum, from which source file it was compiled. We're going to see for which Java version it was compiled. In current case, I used my favorite JDK 8. So why are you laughing? It's my favorite JDK. So in the bytecode, major version is 52, corresponding to Java 8. We're also going to see constant pool. This is the first and the last time you see constant pool. Basically, it is a list of all the constants in the bytecode, strings, numbers, etc. And all the rest of the bytecode just references an item in the constant pool. Why it's the last time? Because it's quite big, it's hard to read references, so I will be inlining them on the next slides in the place where they are used. And here's what we are going to see as a body of this class. Indeed, the holy place is never empty. The ones who say it's empty were right, because in the source code it is empty. The ones who say it is not empty were also right, because in the bytecode it is not empty. So indeed, it depends. What we're going to see here, indeed, there is a constructor. Every class in Java should have a constructor. So if we don't write a constructor by ourselves, it's going to be generated by the compiler on our behalf. And every class should inherit from something. By default, we inherit from Java-lang object, so there should be a super constructor invocation. Here it is. And we cannot just end method with nothing. We should return from the method, so here is the return. This is a simple bytecode of an empty class. And there is a few things more to notice. There is a little link with the source code in the bytecode. More precisely, the only information in the bytecode that exists is so-called line number table. Line number table says, starting from the following bytecode offset instruction, all the following instructions correspond to the following source line. In this particular case, all the bytecode of this method is mapped to the line 1 of our class. Let's move on. Let's have something more complicated. I hope you're warming up, because I will be increasing complexity. So what we have here, we have an outer class. We have an inner, with a private field. We have an inner class. And inside of an inner class, we do increment of the field of outer class. First of all, who thinks that this is a valid Java code? Is it possible to do like this in Java? Yes? Who thinks? I think so. But don't worry, we don't need to guess. We can just compile it. So as we said, Java C example. If there is no errors, then it's valid Java code. We compile it, indeed it compiles, and we could have a look at the bytecode. So we decompile the inner class, and what we see in the inner class, again, my favorite Java 8 version. You might laugh again. Here is method where we do an increment, but can we see increment here? There is no increment here. There is invocation of some strange method. Access $008, like an engine, but without 7, with 8. What this method is, let's have a look at the outer class. What we have in the outer class, here is the method. Notice that our initial method was private. This one is package local static. Notice that it also has some strange keywords that we don't have in Java, synthetic. And this method indeed does an increment. Here is an increment. All that, no, first of all, before all that, why this happens? We first should answer the question why this happens. Well, If we open our Bible, Java language specification, according to the Java language specification, the source code that we just wrote is indeed valid, and Java compiler accepts it. But according to the Java virtual machine specification, it's not valid to access privates from of one class from another class. So, in order to align those two specifications, Java compiler should do the trick. And this trick is, let's generate, on behalf of the user, let's generate package local method that JVM would accept, that JVM would let to call, and that's how we will access the private. All that changed in Java 11 with introduction of nest-based access control. If you take exactly the same example and we'll compile it with JDK 11, here is major version 55, it's JDK 11. It's significantly lost in weight because there is no more such methods generated. There is no more synthetic methods. And this all was possible thanks to introduction of the new attributes, nest members, which says, well, I have some nested classes. Please allow those nested classes to access my privates. And if you look at the inner class, we're going to see the same picture. There is a new attribute, and there is no more any synthetics, no more other changes. And new attribute is nest host, which says, well, I am nested inside of another class. You can, hey, JVM, you can verify this relationship and allow the access to the privates. Right? That's wonderful. That's one more reason, if you was not convinced yesterday to move on a more recent Java version, this is one more reason for you. Let's move on. Let's have a look at some other example. We have two classes, A and B. Class B simply extends class A. And inside of those two classes, we have two methods, one in each. The first class declares a method fun with return type object, and the second method overrides what was declared in the base class. Two return types. The second method overrides with a different return type. Again, is it valid Java code? We don't need to guess. Let's just compile, right? We compile it, it compiles. Yes, it's valid Java code. What we could see in the bytecode. So this time, I don't want to take any bets of old Java and Java versions. Let me try to use Java 18 straight from the beginning to not have any surprises. So major version in the bytecode 62. Let's move on. Here is our method that we wrote. It returns string. No surprises, right? Oh, no, wait. Here is another method that we didn't write in a class B. And it returns object. And the only thing it does, it's also, again, marked as synthetic. And the only thing that it does, it invokes method which we wrote. Why this happens? Why we need this second method? Well, the answer is pretty simple. In all places that do accept an instance of class A, we could simply pass an instance of class B, because B extends A. And all the places which expect instance of a class A should be able to work with the class B. But they do expect the return type of a method to be an object. So here it is. Again, compiler generates on behalf of us some compatibility bridge. Let's move on. Let's have a look on something more interesting, on a pretty simple construction, switch by Enum. Here is a switch. Oh, sorry, here is Enum. It has two constants, false and true. And here is a switch by Enum. It has three cases, false and true, and a default one, because otherwise compiler would complain that we didn't write a default. And that's it. We compile it, we decompile, we look what is inside. Here is the method that we wrote. Here is a switch. All fine so far. But switch is done not by Enum constant, not by the ordinary value of Enum constant. Switch is done by some strange expression. The name of Enum was E, and now switch is done by by something strange. We go into the class $1. In this class, we get a field $switchMap $E. This field apparently an array. We take a value from this array which corresponds to ordinal value of our Enum, and we do the switch by what is stored in the Enum. Let's have a look on this strange class that we never wrote. This time class is synthetic, not entire method, but a class. Here is the field. It's indeed an array of integers. And this class has static initializer. What happens in this static initializer? We take a false constant of the Enum. We take its ordinal. And in the position of this array of the value of this ordinal, we write 1. We do the same for the true constant, but we write 2. And there is some exception handling. This is not very interesting. Why all of this happens? Let me scroll back to our original example. All of this happens because in our current case, both switch and enum are written in the same source file. But if you would write them separately, it would also be possible to compile them separately, and actually to have two different versions at runtime. We can compile switch first, then change in enum, for example, order of constants, or flip them, change order, flip them, or add a new constants, or remove constants. And without any tricks, if you do so, the switch will stop working. If switch does just take into account only original order. So switch somehow should take into account any orders that we would later have at runtime. That's why compiler needs to store the mapping from original order, original enum constants, to the enum constants that will be there at runtime. Here is a little trick that compiler again does on our behalf. Let's move on. So, we've seen this synthetic attribute already many, many times. And if we go into our other Bible, Java Virtual Machine specification, in this specification, we would find the following statement. A class member that doesn't appear in the source code must be marked as synthetic. Or else, it must have some flag set. The only exceptions to this rule are compiler-generated methods. For example, instance initialization method representing default constructor. We've already seen this example. Default constructor generated wasn't marked as synthetic. Class or interface initialization methods, static initialization methods, and implicitly declared members of enums and records. Bam. And a little remark at the bottom of the page that states all of this. The synthetic attribute was introduced back in JDK 1.1 to support nested classes and interfaces. We've already seen that. We've seen why it was introduced. It was necessarily to align Java Virtual Machine specification with Java language specification. And to disallow users from using these synthetically generated members, they needed to introduce a new attribute. You would never be able to access those methods if you just use after completion in ID. They would just ignore them. And interesting conclusion comes out of all this. If you never wrote those methods, those classes, they're probably not significant to be shown to the user. For example, for our code coverage tool. If actually what happens in practice when users see something that they never wrote in the source code, they're surprised. We see something wrong, the tool is broken. So simple, stupid conclusion, JaCoCo should ignore all synthetic methods. And that's exactly what we did since very beginning. We always been ignoring synthetic methods. Guess what happened? Things changed. Let's have a look at more complicated examples. Lambdas, when lambdas appeared in Java language, do you remember?
Java 8.
Java 8, yes, my favorite Java version. Okay, so we have a method exec, it accepts runable, nothing interesting in it, and we have a method fun. Inside of a method fun, we call method exec, and we pass lambda as an argument. Please notice that inside of a lambda, we have a joker, string joker, and please notice that it is on line number 9. If we compile all this and decompile, here's what we're going to see. Exec, method exec, nothing strange in it. Here's our method fun. But where is string joker? It completely disappeared. Where is line number 9? You could see 9 here, but this is not a line number. This is bytecode offset instruction corresponding to the return. There is absolutely no line number 9. Apparently, implementation details of lambdas are the following. The lambda body becomes a new member, a new method in your class with a wonderful name, lambda $fun $0. Here is our joker. And here is line number 9. And please notice that this method is synthetic. Indeed, it doesn't appear in the source code. So what happens is, with our wonderful code coverage tool, well, yes, we ignore lambdas. There is no way to show code coverage for lambdas. And this time, it is implementation details. This time, there is no specification, nor Java language specification, nor Java virtual machine specification, nor even JDK itself. They say that lambdas would be compiled always like this, and the method names would look always like this. Actually, this is even not true. Java uses this naming convention, Kotlin uses another naming convention, Scala uses a third naming convention, and actually Scala changed it 2 or 3 times already. We need to adapt to all this in our bytecode analysis tool. We need to write a dirty hacks like, yes, it is synthetic, we need to ignore it, but only if it doesn't start with lambda $. And then we can get the code coverage for lambdas. That's the features that we implement. Let's move on. At this moment in time, you might start wondering, hey, do you have something non-synthetic? This is not very interesting, right? Well, let's have a look. We already seen enums. What's interesting with enums? Let's try to see. We compile, we decompile. Here is field values in enums. It stores all values of the enumeration. Here is method values. You all, I guess, know this method values. It's this method values, it returns all the values of the enumeration. And in Java virtual machine specification, we already saw that indeed those methods are not marked as synthetic, even though they are generated. Why? Because you users should be able to call those methods. And there is method value of, but unfortunately, you're not interested in seeing code coverage for those methods. Because, well, let's trust the compiler. Compiler does the right job here. Why, for every enum, we need to test exactly the same implementation of exactly the same methods? So we developers of bytecode analysis tool should adapt to this and also somehow realize that, oh, yes, you're looking on the enum. In the enums, we should ignore the following methods, even though they're not marked as synthetic. And here is also constructors that enums have, and static initializer to initialize fields, etc., etc. So yes, some time ago, we wasn't ignoring those methods, and users were not happy with this. We started to ignore them. We didn't realize that there is some users that like to use enums which do not have enum constants, so the enum constructor is never executed. I don't know why they like such enums, but this happens, so we need to also ignore the constructor, and here is how code coverage report evolves. Let's move on. This one should be easy after we saw all the previous ones. I hope you warm it up enough. Records, Java 14. Another wonderful feature appeared in quite recent Java version, records. If you compile such simple record, we're going to see a lot of generated stuff which is not synthetic. We're going to see, a lot. I need to zoom in. Is it visible for you now? I need to zoom in even more. We're going to see field. We're going to see constructor. We're going to see toString method generated for us, hash code, method equals, getter. All of this we need to ignore. But let's move on. Do we have something more interesting than just ignoring the methods? Let's come back to my, again, favorite Java 8 version. Another wonderful feature introduced in Java 8 was switch by string. So here is a switch. It's done by a string. And this switch has 3 cases, right? Case A and case B, and a default. Pretty simple. Let's have a look what happens in the bytecode. Let's zoom in Still probably not visible. Let's move in more. There was only one switch, right? But in the bytecode, there is two switches. Why? We wrote just one switch. What happens here? What's interesting is that the first switch is done by a hash code. Why so? Well, apparently, and yes, here is a switch. Apparently, it's very efficient to implement switch by string using a hash code. With a high probability, all our strings are going to have a distinct hash codes. So if we do a switch by a hash code, we would probably already choose the right case. Of course, it's not always true, because sometimes we can have hash collisions, and some strings might have exactly the same hash code. So we need to do also some comparisons to verify that indeed it's a string with the given hash code and expected string. In this particular case, it happened that I choose two strings whose hash code is exactly the same. So here is the two comparisons for exactly the same hash code. And the second switch is what finally happens. We determine at which string it is. And here is first case, here is the second case, and here is third case. And you can imagine, without anything done on our side, users are going to see all of these branches. They're going to see two switches, and they're going to see all the ifs. And they're going to wonder, why there is 9 branches? I just wrote one switch with 3 conditions, right? So I expect to see 3, not 9. And how the hell I should cover the remaining branches? And all those remaining branches is for the cases when hash code collisions happen. So we also need to write some more sophisticated filters that finds a switch by string, by hash code, and filters it out, saying, yeah, please don't worry, all good, all fine. There is just 3 conditions in your code, no more. Let's move on. Java 12. Java 12 introduced us another wonderful feature, switch expressions. Now we don't need to write a default case anymore if our switch is exhaustive. If we listed, for example, all the possible cases of enumeration, there is no default anymore. Previously we had a default, now we don't. So what happens in the bytecode? Let's zoom in. There are still 3 cases. Why so? We wrote 2. Well, we cannot leave default not implemented. Again, split compilation, what if I recompile it in Enum separately from the switch? A new case might appear and will be triggered at runtime. What we expect to happen? Well, pretty sane implementation generated here. We expect exception to happen. And this exception was for quite some time incompatible class change error. If I'm not mistaken, in Java 21, it's a match exception. Boom. And by the way, speaking about pattern matching, about match exceptions, Java 14 also brought us another preview feature, which is pattern matching. Now we can write inside of an if instance of, do the pattern matching by type, and then operate with this variable as if it is of the following type. If you compile such a simple example, if you decompile it, look inside, what's going to happen? Here I use Java 14 preview features, so minor turns into the magic number 65,000. Here is our example. Here is condition, instance of. That's it, that's what we expected. We wrote instance of, there is instance of. Wait a second, there is another condition. What the hell? Well, apparently you can implement the feature pattern matching for instance of by source to source translation. Exactly the same if you could write it using my favorite Java 8 version using the following construction. There is a second condition. This second condition allows to assign value to a variable that you would be able to use inside of the if body. But this second condition has no sense because it always evaluates to true. This is dead code. And what actually happened with all bytecode analysis tools when this feature was implemented, tools like handbugs, findbugs, etc., JaCoCo, they started to detect this second branch. Findbugs started to complain, well, you have a dead code in your program, whereas we did not. JaCoCo started to complain, well, there is uncovered code, whereas there was no uncovered code. Here it is. So we reported it back to JDK developers. Thanks God, this was a preview feature, so it could be fixed quickly without users even noticing it, and it got fixed. So in Java 16, all this turned into pretty simple, pretty neat construction. So Java 16, no more preview features. Here is our method example, and there is only one condition, exactly as expected. Java 17. We continue with pattern matching. Java 17 brought to us another preview feature, pattern matching for switch expressions. So here is a switch by object. We can do pattern matching by a type. We could also have some conditions. Pretty neat, pretty simple, right? If you compile all of this, what we're going to see, again, Java 17, preview, quite big method. Here is switch. Here is a condition of a first case, body of a first case. If there is no match on the first case, there is use of invoke dynamic instructions, the same instructions that is used for lambdas, but that's not interesting. What is more interesting is line number table. There is a problem with line number table. Can you spot it? I bet no, because I also can't. You need to visualize this first. How to visualize this? Well, you need to step in the debugger through all the lines of this class. And when you do so, you would be quite surprised which lines the debugger highlights. It's not at all the lines you expect. And that was a mistake introduced in this feature. And this time we was quite fast on testing this. We provided the feedback even before this feature was integrated. It was a comment on the pull request. And this problem was fixed even before you received a preview feature. Pretty neat. Pretty nice, right? And here, finally, we come to finally. What an irony. Pretty simple construction, right? It exists since, I don't know, since my favorite Java 8 version and even probably before. We have a try-catch block, and we have a finally. Inside try body, we do call a method nop. Inside finally body, we do call the same method nop. Pretty simple. If we compile it and decompile and look inside, here's what we're going to see. We're going to see 3 invocations of method nop. Wait a second. We saw 2, right? Or 3? Let's check. How many methods nop do we see on the slide? I do see 3. But the third one doesn't count, right? It's a method declaration. So there is only 2. Well, to help us, let's introduce some markers. Let's add an argument. Inside of a try body, we're going to use a string try. Inside of a finally body, we're going to use a string finally. Let's compile this one. Let's change it. Let me highlight it. There is 1 try body and 2 finally. Why this? Well, this is implementation details of try finally. Apparently, on the bytecode level, there is no such construction as finally. The only construction that exists in the bytecode is exception table. Exception table says, if exception happened from the following bytecode instruction to the following bytecode instruction of the following type of exception, then use the following exception handler. This is a catch. How using a catch to implement finally. Finally should be executed when exception happened and when exception didn't happen, right? So here is how we implement finally. In case of exception, we use exception table. Here is exception handler, all good. In case if there is no exception, we still need to insert body of a finally to execute it. So compiler, on behalf of you, does some code duplication. Pretty neat, right? And at home, you might try something interesting with this. You can try to nest try finally inside of a finally. And the growth of this code is, you can understand, it's exponential. So at some moment in time, you will probably reach a limit on the method in Java. That's why it's one of the bad ideas to call try finally inside of a finally. Again, the same thing happens, but we need to write even more sophisticated filter, which will find code duplicates inside of your code that corresponds to the finally blocks and would merge them together. Because, well, users don't expect to test non-exceptional pass, exceptional pass. Sometimes you cannot test all of them because some conditions are only true on exceptional pass, some conditions are only true on non-exceptional path, so we write filter again to pretend, don't worry, there is no duplicates in your code. A little bit of archaeology. Java 1.4, I don't know if you remember it, I do remember. And in Java 1.4, what's interesting, it was possible to implement try finally without duplication. Apparently, it was enough to use exception handler and a neat feature of Java 1.4, GSR and thread instructions. Java subroutines. Apparently in Java 1.4, it was possible to have functions inside of functions. If you're interested in this feature and would like to learn a little bit about archaeology, I could recommend another presentation of my friend about bytecode verification. But let's move on. And now I hope you really warm it up. Are you? Let's have a look at final examples, and let's embrace them. Try with resources. Pretty neat feature. When was it introduced? If you're going to say Java 8, your favorite Java version, no, you're going to be wrong. Try with resources were actually introduced in Java 7. Try with resources are pretty nice. They allow us to declare a resource, to say this resource is closable, implement a method close, and to use try with resources construction, passing an instance of our resource with a guarantee that once we don't need this resource, the method close is going to be called and can close all the files, all the connections to database, etc., etc. Right? Pretty neat feature. Without it, it was quite cumbersome to write exception handling when resources are involved, right? What happens if we compile this source code? We're going to get such a big piece of the bytecode. You probably couldn't even see what's written. At least I could not. Let's zoom in. Does it help? Well, no. Let's zoom in more. There is 4 times call of a method close. Why 4 times? Well, pretty simple. We know that we need to close the resource. So let's call the method close 4 times to be sure that we closed the resource, right? No, probably not. We need to look closer. There is also some checks if something is not null. It's quite hard to investigate looking on the bytecode. So let's try to find some clues for this. And this time, I don't know why. I don't know why for lambdas there was no clues in Java language specification. But in case of try with resources, there is a clue in the specification. The meaning of a basic try with resources statement, like the one we've just seen, is given by the following translation to a local variable declaration and a try catch finally statement, and the following piece of code. So the example that we've just seen is semantically equivalent to this source code. It does exactly the same thing. At this moment in time, you could ask, can I prove it? Well, I can prove it. Let me try. So what we have here? I have fun1. It's exactly try with resources that you've just seen. I have fun2. It's exactly the big biz that we also just seen. If we compile fun1 and decompile it, what's the name of the class? Example. And save result of decompilation in 1txt. If you do exactly the same with fun2, and save result of decompilation in 2txt, and we try to look at the difference. Something didn't went right. Let me try again. Example, and fun2, example. 1 and fun2. Right. Why you're not helping me? We did not use it my wonderful options for the decompilation. -weaverbus -p show me everything. So we really want to see everything what happens here. Bam. They are different. But how they are different? Of course, modification time changed because I haven't done compilation at exactly the same time. Of course, they are produced from two different source files, but that's pretty much it. The rest is line number changes. Of course, they have different line numbers. But all other bytecode is exactly the same. Only line number changes. So if we go back to this example, compilation of this code on the bytecode level is a pure equivalent to try with resources. What does it mean for bytecode analysis tool, like our code coverage tool? We cannot distinguish those two from each other. They're identical. So what we do, yes, we do implement filter which finds such a pattern in the bytecode and says, well, this should be try with resources. And we filter it out without showing all the branches, pretending that there is no code duplicates, etc., etc., etc. But if you will write such a source code, we will also find try with resources in the bytecode and filter it out. And you wouldn't see coverage for the such code. Thankfully, it's all right, because if you was able to write such a source code, then you probably know how to write it, then probably you don't need to test it. If it compiles to exactly the same bytecode as compiler does, again, you don't need to test it, so you don't need to see code coverage for it. And so far, nobody complained, so we are safe. Let's have a look what happens in this source code. Why try with resources compiles like this. There is a try catch. If exception happens, we need to remember this exception. There is a finally, and you remember from the previous examples that finally are gonna be duplicated on all the paths of all the exceptions, and plus on non-exceptional paths. And inside of this finally, we do some ifs. In case of exception not happened, we need to close the resource. And if during closing of resource exception again happened, we need to attach one exception to the other. In case if there was no exception, we just need to close the resource and just let exception propagate. And well, we, for some reason, check whether the resource is null or not. But in this particular case, compiler knows that it cannot be null. So there is a dead code. There is another dead code. If exception happened and we inline finally inside of a catch, we don't need this condition, because exception always happens in the catch. We just catch this exception. So there is another dead code. Again, all bytecode analysis tool would complain on this example that there is some dead code. And this is exactly what was happening. So GDK did some improvements, and Java 7 try with resources was introduced. With Java 8, it was improved. Instead of 4 ifs that we've seen before, we now get 2. And future improvements, if we use Java compiler 11, but still target Java 8, we're going to see 0 ifs. That's neat, and this is exactly why we need to test our tool on such wide range of the compilers, because, well, even from compiler version to the compiler version, the patterns that we are looking for, they are changing. So that's exactly what happens. We implemented the filter, and we pretend that, well, you do not have such a big piece of code under the try with resource. Here we come to conclusion. Source code is not bytecode. Please be careful. What you see in tools that are based on the bytecode analysis is not at all what you write in the source code. Please be careful. And the source code is not actually what is gonna be executed. JVM is gonna execute bytecode. And even this is not true. Because, you know, there is JIT is gonna come, JIT is gonna compile bytecode to the native code and execute even not a bytecode, but the compiled native code. So please be careful. There is dragons. We've seen that quite a lot of information is generated on behalf of us. This could lead to not only strange code coverage reports, this could lead to degraded performance in the places where we don't expect it, like with nested classes, there is additional methods, etc. And, well, bytecode-based tools such as findbugs, huntbugs, JaCoCo, they have to guess what they see in the bytecode. They have to guess what user wrote in the source code. So please bear with us. We have to live with this. We developers of those tools have to adapt, have to develop some filters for you. And you developers, users of those tools, you also should live with it. So please, next time, when you find something strange in code coverage tool or in your favorite bug hunting tool like FindBugs that analyzes bytecode, please don't come to the developers of this tool screaming, oh, it doesn't work. No, it works, but it works just on a different level. Instead of saying it doesn't work, now you know how to investigate. So you could compile, decompile, look inside, and come with a report saying, look, what I found, pretty neat, pretty interesting. Could you please do something with this? And that's it. Thank you for coming. And if you have any questions, we don't have time, but you could catch me outside and talk about whatever you want.